This is section 9.2, antenna radiation characteristics. Before we get started with the radiation characteristics, we need to know that we're looking at an antenna. We're analyzing it as if it was coming from a single point in the spherical coordinate system. We'll be analyzing it. And when we look at its waveform, like its radiated wave, we're looking at it from a far field region, meaning that its radiated wave, although it's spherical in nature, we will see a planar wavefront. So that'll help our calculations. And so from the previous lecture, we have the time average pointing vector, or the power density, that has the direction of r hat, so radially away from the center, and then the magnitude is power density. That's in watts per meter squared. Okay, so then we have the normalized radiation intensity. This one is a sum power density over the maximum power density, and that's unitless because it's just the ratio of power densities. And then we also have the solid angle of a sphere, which is 4 pi steradians. Steradians is the angular measure of our spherical coordinate system because it has two angular components to it. Okay, so let's move on to 9.2. So what do we want to find? We want to find an antenna radiation pattern, or the radiation pattern of an antenna. And so the reason we want to find that is because we want to find we want to make a 3D plot of the strength or the power density of an antenna at a fixed distance from the antenna. We can also make a 2D plot, and this will be with a ranging theta value or a phi value, so just different angles of our antenna. We'll measure the strength of it in order to see how our antenna works in 3 dimensions, and we're also going to characterize that with a pattern solid angle, but that's later on. So in order to find that plot, we're first going to start by finding the power radiated by the antenna, but in order to find that, we're going to do a differential power radiated, so we can derive that. This differential power radiated is going to be equal to the average power density dotted with a differential area vector. So just a really tiny area. When we do the dot product of that, we can actually simplify it by taking out the r hat. So we're going to be left with the average power density times r hat, and then a differential area. The dot product of these two, the directions will cancel out. This has a magnitude of 1, so we're going to be left with just the a power density times a differential area. Okay, and the units of that are watts per meter squared. An area is meters squared, so obviously we're going to be finding a differential power with this. So let's simplify that, let's expand that. Not expand it, let's take the integral of that to find the power radiated. So the power radiated, if we take the integral, will be a double integral because we're in an area. This goes from 0 to pi and 0 to 2 pi because this area, let me write that over here. The dA is equal to r squared sine theta d theta. This is just the differential area for a spherical coordinate system. So that's the reason we're integrating from 0 to pi, 0 to 2 pi, because theta and phi. Okay, so, and then what else do we have? We have the power density, which varies with the range, the theta angle, and the phi angle. And then we have the differential area. Okay. We said that this differential area is this, but we can also see that a differential, what is that? Angle, solid angle, that a differential solid angle is equal to a differential area over r squared. And that's because we're taking the r squared out of this to get rid of the range component of it, and we just have the area component of it. So that makes sense. We can solve for this dA, and then we're going to be left with d omega times r squared, and we can plug that into over here. So we have the power radiated is equal to the double integral. I'm going to write the limits right now. R theta phi. And then we said that we're replacing this with d omega. Oh, before d omega, we're replacing it with r squared d omega. Okay. Now, this power density, I can actually expand that into being the normalized radiation intensity times a maximum power density. And I'll actually write that over here, because that's going to be our final answer. So that power radiated from an antenna is going to be a double integral. The limits of integration for this, we're in d omega, which is in steradians, from 0 to 4 pi, because that is the solid angle of a sphere. Okay, from 0 to 4 pi. And then we're replacing the s r theta phi with this. We're going to replace that s with the normalized radiation intensity times the maximum s. But this maximum s does not depend on theta or phi, so we're going to bring that out. So we're going to have an s max. And then this r squared does not depend on theta or phi, so we're going to have an r squared. The double integral again from 0 to 4 pi of the normalized radiation intensity, F. And that's just d omega. Okay. Wow, I wrote that big. Okay. Okay, so we found an equation for our power. And if you solve for the units, watts per meter squared times meter squared, this is an angle. So we have, this is not an angle we solved. We took out that component. So we have the power radiated. Okay, now we can move on to plotting. So when we're plotting, we're gonna plot the normalized radiation intensity. We're gonna do a 2D plot, but you can also do a 3D plot where you're changing your theta and your phi value. But we're just gonna do a 2D plot when we're changing our theta value. So we're plotting the normalized power intensity, but we're plotting that in decibels, or normalized radiation intensity in decibels over a theta. This is 0. Actually, before we do that, let's write the equation for our pattern solid angle. So our pattern solid angle is equal to the double integral of 0 to 4 pi of the normalized radiation intensity. Okay. So this is the equation for a pattern solid angle, which characterizes, it'll tell us the three-dimensional graph of our antenna, kind of. So before we do that, this normalized radiation intensity for an isotropic antenna will be 1. So for an isotropic antenna, we're gonna have a pattern solid angle of 4 pi, because we have 1 inside and then we integrate that 0 to 4 pi, we're left with 4 pi. Okay, for anything else, we're gonna have a pattern solid angle smaller than 4 pi. And so a pattern solid angle, that's a solid angle. 4 pi, that's a sphere. So anything smaller than that, we're gonna get a cone. Okay? So we have this plot, and then
Okay, so from this plot, what we're interested in is we're interested in the points that are 3 decibels less than the top of the plot, which is 0 decibels because this is normalized. And so we're looking for something that is 3 decibels less, and that'll give us the half power. And we're gonna call that the half power beam width, with these being the half power angles right here, the angles that correspond to these points.
Okay, so that would be the half power beam width. And what that allows us to do is if we have 2 beam widths in 2 planes, so let's say we have the XZ plane.
I'll just write this down before. Let me write this down here.
So we're gonna find the pattern solid angle is equal to the beam width in 2 planes when they share one axis. Okay, so we're doing this in the XZ and YZ planes. So XZ and YZ. So if we have a beam width, let's say it's like this wide, right? In the XZ plane, and then in the YZ plane, we have another beam width that's this wide. This pattern solid angle, we can approximate it using those 2 beam widths. And when we approximate a pattern solid angle, we're going to get a cone. So if we kind of have the width of the cone in one direction and the width of the cone in another direction, so we can kind of just revolve it, and then we're left with a cone showing the kind of like the direction that our antenna is radiating in. If it's a cone, then it's radiating one way, and if it's a whole sphere, or we can see how wide the radiation of our antenna is. Okay, so yeah, those beam widths come from the half power beam width of our plot. And okay, so next let's move on to the directivity of an antenna. So the directivity is defined as the directivity is equal to the maximum normalized radiation intensity over the average normalized radiation intensity in all directions. And this is equal to 1 because the maximum radiation intensity, that's normalized, so that's just going to be 1. And then over here we have 1 over 4 pi times this, which is theta phi d omega. We see that this is actually just the pattern solid angle. We're multiplying it by 1 over 4 pi because it's a spherical coordinate system, and we're getting rid of the angular part of this. So we have 1 over 4 pi. Right, would it be, no. Okay, now this, we can replace this with our pattern solid angle that we found over here. So we're gonna be left with 4 pi over the pattern solid angle. This is one of the definitions for our directivity. And what that tells us is when we have a narrower pattern solid angle, a narrower pattern solid angle would mean anything less than 4 pi, because the pattern solid angle of a sphere we said was 4 pi. Anything less than 4 pi, meaning that our cone is smaller, will be a smaller value here, meaning that this will be bigger because that's on the bottom. So our directivity is going to be bigger. So the smaller a cone that our antenna is radiating in, the bigger the directivity of it. And so that can go up to infinity. The smallest directivity can be 1. That would be for an isotropic antenna. Okay, so we can also use, from this Prad, from this radiated power equation, we can replace this part of it with the pattern solid angle. So what we would be left with would be, I should probably write this down here, Prad is equal to the maximum power density
times r squared times the pattern solid angle. And if we solve for that pattern solid angle, we get the pattern solid angle is equal to the radiated power over the maximum power density, S max, times r squared. Okay, we can plug that into over here. And so we get another equation for our D, saying that it's equal to 4 pi times r squared times S max over, over the power radiated from our antenna. Okay, so this is one of the equations for D. And that's going to be interesting because next up, we're looking at before I move on, this is also equal to the S max over the S average. Why? Well, that's a good question. The average power density, we can look at it as the power over the surface area of a sphere, right? So the power density average, we can see the average power, which is the power radiated out of an antenna, over 4 pi r squared. And what is that? That is the surface area of an antenna. So, I mean the surface area of a sphere. And so that gives us an average power density in a sphere. Okay, yeah. Now, moving on, we're gonna look at the gain of an antenna. So the gain accounts for ohmic losses in an antenna. So it's related to the directivity, but before we start, we're gonna look at the radiation efficiency, which is given by this Greek letter. That's gonna be equal to the power radiated over the transmitter power. Okay, so the power coming out of our antenna versus the power that we put into our antenna. So this is kind of taking into account the power lost in our antenna, in a way. So the gain, we're going to define it as 4 pi. I should move this down. So the gain is defined as 4 pi r squared, maximum power density, over the transmitter power. Okay, so if we look at these two, they're very similar. They're related by the power radiated and the transmitter power. Okay, so we can use this radiation efficiency to find an equation that relates these two, because the radiation efficiency takes into account the power radiated and the transmitter power. So let's say we solve this, let's say we put the transmitter power over here. We can replace this P rad with, let's say, if we put the transmitter power over here, let's say we replace this P rad with the directivity times the transmitter power, and then we can move this over to this side, and then we would have a transmitter power on the bottom, and then we move the radiation efficiency to this side, so we would be left with a gain is equal to the radiation efficiency times the directivity. Okay, and that just kind of relates the two. Okay, so this is telling us that the gain is taking into account the ohmic losses in the antenna, and the directivity does not. So yeah, another way to find the radiation efficiency is we're gonna use this equation, right? So we have the P rad, and the transmitter power is the radiated power plus the power lost. Okay, using the equation for the radiated power, just your power equation, 1/2 I squared times R, we can solve for the R loss and the R rad, and we can determine that this is equal to R rad over R rad plus R loss. So the radiation efficiency of an antenna is going to be equal to the radiation loss of the antenna over the radiation loss plus the radiation resistance over the radiation resistance plus the loss resistance. That will be it. Thank you.